Lesson 6, Metabolism, Energy, and Enzymes. What is energy? We've all used the term energy. It's really kind of an abstract idea. In this lesson, our definition of energy is the ability to do work and bring about change. All living organisms must be able to extract energy from their environment. Organisms need energy to maintain organization, for growth, for development, reproduction, and also to maintain homeostasis. In fact, this looks a lot like the list we saw in Lesson 1, our characteristics of life. They all require energy. There are different types of energy. Kinetic energy is the energy of motion. Anything that has mass and movement possesses energy. So mechanical energy. Sunlight is also a type of kinetic energy. Another type of energy is potential energy. This is stored energy, energy that's not being used right now, but is available for use at another time. The most important form of potential energy that we will be interested in is chemical bond energy. Recall back in Lesson 2, it requires energy to form chemical bonds, and then that energy that was put into the formation of the bond is stored chemical potential energy. Energy is governed by the laws of thermodynamics. The first law of thermodynamics tells us that energy cannot be created or destroyed, but energy can change forms. In this diagram, sunlight, which is a form of kinetic energy, is transformed into chemical bond energy or potential energy. This occurs during the process of photosynthesis. Organisms that are autotrophs can capture solar energy, use that to form new chemical bonds to build sugars. Down at the bottom of the screen, this is the summary equation for photosynthesis. 6 molecules of carbon dioxide plus 6 molecules of water plus energy from the sun, and this can eventually be converted into the sugar glucose. Chemical bonds can then be broken, so that energy that was used to form the chemical bonds can be broken and released, and so we can convert that energy from potential energy back to kinetic energy. So this is what happens when we consume the carbohydrate that was produced by the autotroph. That carbohydrate can be broken down in our muscle cells, for example, and that energy can be released and used for other things. This is the summary equation for cellular respiration. We really take that photosynthesis reaction and flip it over. So we can begin with glucose. We can break that down into 6 molecules of carbon dioxide, 6 molecules of water, and the energy from those chemical bonds can be released, converted back into kinetic energy. So energy has not been created or destroyed. However, we can change forms of energy. The second law of thermodynamics tells us that even though energy can change forms, it cannot change forms without the loss of usable energy. Energy is not going to be destroyed. However, we do have some loss of usable energy. Energy is lost in 2 ways, heat and entropy. In this diagram, we see solar energy. Part of that is absorbed by the autotroph, the tree, but much of that is radiated away and lost as heat. That heat is not useful. The portion of the energy that is absorbed by the autotroph, the tree, can be converted into chemical energy. As a heterotroph feeds on that, again, some of that is lost as heat. Only a portion of that energy can be converted from chemical energy into the mechanical energy in the body of the heterotroph. So at every step of the way, whenever we have energy conversions, we have some lost heat. This one's really easy to see. Whenever you start your car and the engine block becomes hot, that heat is lost energy. Only a portion of the energy in those bonds of the gasoline is converted into kinetic energy and moves your car. Much of that is lost as heat. Entropy, again, this is a little bit abstract, but entropy is the amount of disorder in a system, and that disorder represents energy that is not useful. So the glucose molecule we mentioned just a moment ago, C6H12O6, that is a very highly organized molecule. It contains a lot of potential energy in those chemical bonds. As that is broken down into smaller molecules, that is increased disorder. These molecules are less organized, they have less potential energy, there are fewer bonds, and so that increased disorder is an increase in entropy. And again, entropy is energy that is not useful in a system.